Okay, so today we're going to start going into our first unit, which is energy and power. We're going to start things off pretty basic by looking at simple machines and how we can use those to build more complex systems. So simple machines are basically just mechanisms that manipulate the magnitude of force and distance. So however much force or distance we're putting into a system, a simple machine can change that. So there are 6 classical simple machines that most people would consider. We've got a lever, a wheel and axle, a pulley, an inclined plane, which, basically just a ramp, a wedge, which is if you took an inclined plane and used it as the object that's being pushed into something. And then you also have the screw. And that's like you take an inclined plane and you wrap it around like a pole or something like that. So in all of these situations, we can see where there's a force acting and how the simple machine can change the amount of force required or the distance. So a simple machine can change both the magnitude and direction of forces. Oops. So take, for example, the pulley. On a pulley, you would pull down and to the right, and that causes the block to move upward. It redirects the force in a positive direction, whereas you're pulling down. So we'll see that in a lot of situations where, a lever is going to require you to use a smaller magnitude of force or a greater distance. And the way that we can use these simple machines to create more complex systems to effectively perform certain tasks is by analyzing their mechanical advantage. And we'll simply abbreviate that as MA. Mechanical advantage can be defined 2 ways. There are 2 ways that we'll look at it. So it is the ratio of the magnitude of the resistive forces or the resistance forces to the effort force. Okay, what do those words mean? So the effort force we can think of as like the input force. It's what you're putting into the system. The resistance force, we'll also see this called the load, is what you have to overcome in order to achieve your goal. Okay, another way that we can define the mechanical advantage is by looking at the distance traveled by those forces. So we can say it's the ratio of the distance traveled by the effort force to the resistance force. So they switch places when we're looking at distance versus magnitude of the force. There are 2 situations that we'll see. We'll either have a mechanical advantage greater than 1 or a mechanical advantage less than 1. Mechanical advantage could be equal to 1, but it's not super interesting, so we won't talk about it. If the mechanical advantage is greater than 1, that means that you need a lower effort force Oops. We'll just rewrite this. Effort force we can call FE, resistance force we can call FR. We'll need a lower effort force to overcome the resistive force. But simultaneously, we're going to need to cover a larger distance with that effort force. So we have to increase DE, which is the distance covered by the effort. If your mechanical advantage is less than 1, you'll be increasing your effort force to overcome the resistive force, but you don't have to travel as far, right? You can decrease your effort force, the distance that your effort force travels. But mechanical advantage, regardless, is always going to be greater than 0. We're never going to see anything negative or equal to 0. And that just means that one way or another, you're going to have to sacrifice either force or distance. Okay? Another way that we can analyze systems in relationship with this mechanical advantage is by looking at the amount of work that's put into the system. Work is a measure of the amount of energy that is transferred when a force acts on an object. So work, energy, those are kind of synonymous. We will say that work is equal to the force applied times the displacement that is parallel to the force. So that's parallel to the force. Okay. So if I have a pulley and the box is moving up, right? My force is pulling down like this, I'm only going to look at what's happening in the vertical direction because the box isn't moving to the left. And we'll see an example in a second. So work, what's interesting is that work is going to remain constant for a system as long as you're accomplishing the same goal, doing the same task, regardless of the mechanical advantage of that system. Okay, so you can either increase the force and decrease the distance, or decrease the force and increase the distance. And that means that force and displacement in this equation have an inverse relationship. So let's take a look at an example for work. A woman applies a constant 100-pound force to a box at a 20-degree angle as measured from the horizontal. So let's draw a quick picture. Got a box. We're going to apply a force at an angle 20 degrees to the horizontal of 100 pounds. Okay, and then it's going to slide across the surface and end up 12 feet away from where it originally was. Okay, now what you'll notice is that only some of that force is actually going to cause the box to move, right? Any of the force that's directed into the ground isn't going to affect the box, right? It's not going to cause anything to move. But the part of the force that's pushing it to the right, that's what's actually doing work. So that's the force we're interested in. So what we need to do is think of force as a vector. So force is a vector, and this is just a simple right triangle because horizontal and vertical are perpendicular. So if the hypotenuse of my right triangle is 100, and I'm looking for the force in the horizontal direction, because the vertical direction is not going to do any work, we can call this Fx. And here's our angle, just so we remember, that's 20 degrees. We can say that we have the adjacent side, hypotenuse, so that's cosine of 20 degrees is equal to adjacent over hypotenuse, or Fx is equal to 100 times the cosine of 20 degrees, whatever that is. Okay, and so that's the amount of force that's actually doing work. And so now we can solve for how much work is being put into the system. So that's the force in the horizontal distance times the displacement in the horizontal direction, which for us is 100 times cosine of 20 times the displacement 12, and that ends up being about 1,128 foot-pounds. Weird customary units. We'll kind of go back and forth between units, but you have to be able to use both because some engineers still like to use customary. Okay, and then there are 3 more things that we want to look at when we're analyzing a system. So obviously the world is not perfect, okay? You can have a situation where you do all these calculations and set it up and then it doesn't work, right? And that's because there's friction in the world. There's heat loss, there's sound, we're losing energy. So the calculations that you did initially are for the ideal mechanical advantage. And this is a theory-based calculation if everything went perfectly, where frictional losses are neglected. So any energy loss due to heat, friction, sound, deformation, that's all ignored. Okay. And the way that we can calculate the ideal mechanical advantage for a system is by looking at the ratio of the distance traveled by the effort force and the distance traveled by the resistant force. And we'll just call that dE over dR. Now, in the real world, there is friction. There are things that will happen to your system to where you won't get the exact thing that you got in your calculations. So actual mechanical advantage is more situation-based, and we'll call that inquiry-based, because we want to learn things from the system and see how much is actually required in order to complete the task. So frictional losses here are considered. And that includes, heat loss, sound. The easiest thing for us will be just friction. And the actual mechanical advantage is the total resistance force, to the actual effort force that is required when you actually perform the action. So not just what you've calculated from the ideal mechanical advantage, what actually is required, okay? We'll still just call this FR over FE, but we'll make the distinction when we're actually working through the problems. And then the last thing that we want to look at is efficiency. Efficiency is a way that engineers can see how much energy are they getting back from their system, okay? So how effective is it at converting energy? So efficiency is the ratio of useful energy output to the total energy input. So we're basically just comparing what comes out to what went in. And the easiest way to do that in this class is just to look at the ideal mechanical advantage and the actual mechanical advantage. So the useful energy output, that's more in line with the actual mechanical advantage. And the energy input would be the ideal mechanical advantage. Okay. Now, there are multiple ways that we can talk about ideal mechanical advantage, actual mechanical advantage, efficiency, that'll be specific to different types of simple machines, but we'll get into those as we go through each simple machine. I have posted a blank version of this notes on Schoology, so you can fill that out at your own pace, and I will post a cleaner version of my notes probably on Monday. So I'll redo this and make it nicer.